welcome all of you to this session on applied thermodynamics. Today we shall be discussing on the first law of thermodynamics by solving some numerical problem. So let us see what's in store for us. So you can see the problem mentioned in the screen. A slow chemical reaction takes place in a fluid at the constant pressure of 0.1 megapascal. So the pressure remains constant throughout the thermodynamic process. So it refers to an isobaric process. The fluid is surrounded by a perfect heat insulator during the reaction, which begins at state 1 and ends at state 2. Now from this information you can easily understand that the process which has the states of 1 and 2 is obviously an adiabatic process since uh, the fluid is surrounded by a perfect heat insulator. That means no heat can pass through or no heat can be transferred, so no heat transfer is allowed. That means it is an adiabatic process. So for the process 1 to 2, it is an adiabatic process. The insulation is then removed and 105 kilojoule of heat flows to the surroundings as the fluid goes to state 3. So for the process 2 to 3, that means the initial state being 2 and the final state being 3, here you can understand that 105 kilojoule of heat is flowing from the surroundings. Okay, flowing to the surroundings. That means heat is getting lost here. The following data are observed for the fluid at states 1, 2 and 3. So this is your data. The volume and the temperature is given here. Now you need to calculate E2 and E3 if E1 is 0. So in the previous lecture, while describing the concept of first law of thermodynamics, I have always used this du. I have never used this de term. So I need to clarify myself why I haven't used this e and what this e term means here. So please don't get confused. I am here to explain. Now, while discussing about the concept of stored energy, I have told you that energy can be stored in two different ways. One is the macroscopic mode and the other one is the microscopic mode. So this kinetic energy ek and this potential energy ep are the forms of macroscopic energy, whereas this u is the form of microscopic energy. Now if you are interested to calculate the change of this energy, you will find that this part, the change in the macroscopic macroscopic stored energy is very less. It can be neglected, so it becomes 0. We neglect the changes unless it is a very huge change. Okay, so what happens? So for that case, this d and du becomes the same thing. Okay, so please don't get confused. You can use du or de, whatever you want. So for any process 1 to 2, the change of internal energy is u2 minus u1. Similarly here, while using the term e, you can write the change in internal energy will be e2 minus e1. So as there are three specific states, that means you will have three specific internal energies. Okay, so e2 and e3. Now the question is that so let us move to the solution part here. So e1 is given as 0. Now certain data and information is given to you through this problem. so that you can calculate this E2 and E3. So the first information is that I have already mentioned you, it is an isobaric process. So, and the process 1 to 2 is an adiabatic process. Okay, so I am taking some time to write up all the information in a certain format so that it becomes easy to understand, and it will be good for myself to explain also. So let us write there. So I have written down all the informations which I have found from this problem. So you can see that the processes 1 to 2 and 2 to 3 are isobaric process. So the pressure remains constant throughout the entire process, and the process 1 to 2 is also adiabatic. Now the constant pressure is 0.1 megapascal, and in the case of process 2 to 3 you can see that 105 kilojoule of heat flows to the surroundings. That means heat is losing. Okay, heat loss is taking place from the system, so there is a minus provided here. Now your objective is to calculate this E2, E3 and E1. So we will be using the concept of first law of thermodynamics. That is quite easy to understand. So let us apply the first law of thermodynamics for the process 1 to 2. So it will be Q1 to 2 equal to, so I am writing dE here so that it is easily understandable to you. So I'm writing dq, I'm sorry, so d, just give me a little bit of time here. So dq is equal to de plus de plus d plus dw. Okay, so this is for process 1 to 2 and this is for process 1 to 2. Okay, now I have already mentioned that the process 1 to 2 is an adiabatic process, so this becomes 0. Okay, so there is no heat transfer, so this becomes 0. Now we can write this E1 to 2, that is DE1 to 2, that is a change of internal energy. So we can write this change as E2 minus E1. Okay, so this E2 minus E1, so 0 is equal to E2 minus E1 plus dw12. Now you know the formula of displacement work in an isobaric process, so I'm not going into the description of that formula. I am just writing it down. It will be P, that is PC for constant pressure. It will be V2 minus V1. Okay, final volume minus initial volume. So integration of PdV, and you know dV integration integrates as V. So the upper limits and the lower limits are V2 and V1. So ultimately we get the result. So putting this constant pressure as 0.1, V2 as 0.3 and V1 as 0.00003, we will get the result of this work transfer as it will be 29.7 kilojoule. So I have calculated it early, so this is 29.7 kilojoule. So you can write now this as 29.7 kilojoule. Now this E1 is already given as 0, so you can write this E2 is equal to minus dw 1 to 2. So which is equal to minus 29.7 kilojoule. So that's how we can easily calculate the value of E2. Now let us see how we can calculate the value of E3. Okay, so let us just remove this. So when I am trying to calculate the value of E3, I am applying the first law of thermodynamics for the process 2 to 3. So you can see that dq for the process 2 to 3 is equal to de for the process 2 to 3 plus dw. Now, as mentioned in the problem, you can easily understand that this heat transfer for this process 2 to 3 becomes minus 105 kilojoule, and the work done, since it is an isobaric process, you can calculate the work done by the same formula. Now you know the value of this PC, which is 0 0.1. You know the values of V3, which is 0 0.06 meter cube, and the value of V2 is 0 0.3. So by the calculation, it will be uh, minus 24 kilojoule. Okay. Now for this equation, that means when I am applying the first law of thermodynamics for process 2 to 3, it is quite evident that this dq 2 to 3 is minus 105. I have already expressed why this minus is here, and d e 2 to 3, that means change of internal energy for process 2 to 3 will be 3 minus e2. Now we have already calculated e2 as minus 29.7, so this equation turns into e3 plus 29.7. So now putting the values, it will generate an equation like this: 105, that is equal to dq 2 to 3 e3 plus 29.7 will be plus 29.7, and for work done it will be minus 24. So ultimately the result would be minus 110.7 kilojoule. I hope you have understood the application of first law of thermodynamics here. By this problem, there was a confusion regarding U and E. We generally use U and E. We can use any of this, okay? But much more specific it would be if you write E rather than U, because E refers to the total storage energy. So whenever we are dealing with thermodynamics, mm, since we are discussing with the first law of thermodynamics, since it mentions the energy conservation, so this E would be much more specific. Okay, so with that, I think this problem is done with, and we will be moving on to the next problem. So let us check out what is the next problem, and so let us move on to that. 1.5 kg of liquid having a constant specific heat of 2.5 kilojoule per kg Kelvin is stirred in a well insulated chamber, causing the temperature to rise by 15 degrees Celsius. Find the change of internal energy, which is referred here as delta E, and the work done for the process. Now this process is happening in a well insulated chamber. That means there is no heat transfer in or out of the system. So this dq, so this dq is nothing but 0. Okay, since there is no heat transfer, this dq is 0. Now we know the statement of first law, so it is dq equal to du plus dw. So you need to calculate the du, which is referred to delta E here in this problem. Now, all the change of internal energy which is happening here, it can be calculated by a simple formula, which is mc, C being the specific heat, M being the mass, and delta T being the change of temperature. Since the temperature is rising by 15 degrees Celsius, we can write this delta T as 15 degrees Celsius. Since it is a difference of two temperatures, in kelvins it will be also 15. Okay, so we can calculate this du from the above formula. So this du becomes mc delta T. You can also use CV here. Since the volume of this fluid remains same, you can also use this volume constant. Okay, so you can also use CV. So this since this m is given here as 1.5, so it is a little bit of calculation which will give you the value of 56.25 kilojoule. So it is just plain and simple multiplication. So this is the change in internal energy caused by the stirring action. Now, since a stirrer from the outside or from the surroundings is being used to heat the fluid, it is quite obvious that the work done is by the surroundings on the system. Since the work is done by the surroundings on the system, we will know it will be a negative work. So, and this dq is 0 because here the chamber is well insulated. That means no heat transfer can take place. So dq becomes 0, and this delta E we have already calculated here by this. It will be 56.25 kilojoule, and you know, if this dq becomes 0, then du obviously will be equal to minus of dw. So from this understanding we can calculate the value of dw as minus 56.25 kilojoule. So the work is done by the surroundings on the system. So this is the important understanding you need to make from this problem here. Okay, so the energy storage which is getting increased, it is because of the change in temperature. So you should always remember that internal energy is a function of temperature only. I have already mentioned in the previous lecture. So this was the problem which was very simple. Now let us see the next one. So here is the problem number 3. The properties of a certain fluid are related as follows. U is equal to 196 plus 0.718 T, and PV is equal to 0.287 T plus 273, where U is the specific internal energy which is expressed in kilojoule per kg, and T is in degrees Celsius, P is in kilonewton per meter square, that is kilopascal for you, and V is specific volume meter cube per kg. For this fluid you have to calculate the CV and CP. Now if you remember, CV resembles to this specific formula and CP resembles to this specific formula, where U is the specific internal energy and this H is the enthalpy. Now this H can be written as U plus PV. Now it is very plain and simple problem of differentiation. So when this volume remains constant, you need to derive, you need to do a differentiation of this U with respect to T. So let us see how it can be done. So as you can see, u was equal to 196 plus 0.718 t. So this was in the problem, it was expressed in small t, but in the formula we have written it via a capital T. So this t and this t are the same thing. They both represent the temperature. Okay. So I hope you are not having problem in understanding it. So when we are doing a differentiation of this u with respect to the temperature, it ultimately gives the value of 0.718. Okay, so it is very simple. So it becomes, so you can write this CV as 0.718. Okay, I believe you have understood it easily. So the unit will be kilojoule per kg Kelvin. Okay, the unit will be kilojoule per kg Kelvin. Now we need to do the calculations for CP. Now for CP, you can find that CP is the change of specific enthalpy with respect to the temperature when the pressure is kept constant. Now U is given here by this formula and PV is given here by this formula. Now you can easily convert or add up these two, and ultimately you can get the requisite data. So let us see after doing the addition what kind of value we get here. So simply adding up u, which is given here as 196 plus 0.718 t, and pv, which is given as 0.287 into t plus 273, we get this. Now this part will be useless. This is irrelevant here because you are going to perform a differentiation with respect to temperature. So del H del T with respect to the constant pressure, it will be 1005 because these are constant. So when we perform the differentiation, this becomes 0, and with respect to T it will yield 1.005. So the CP becomes 1.005. The unit remains the same, that means as it was in CV, kilojoule per kg Kelvin. So these two values of CP and CV, you need to remember it very well, because in numerous problems you will see the useful you will see that CP and CV becomes very much useful. So you have to keep in mind these values. CV is equal to 0.718 kilojoule per kg Kelvin and CP is equal to 1.005 kilojoule per kg Kelvin. So these two information, you need to remember it very well. Okay, so I hope you have understood the whole problem. It was very easy. Now let us move on to the next one. Let us see what is the fourth problem here. So as you can see, the problem number 4, a gas undergoes a thermodynamic cycle consisting of three processes, beginning at an initial state where P1 is equal to 1 bar, V1 is equal to 1.5 meter cube, and U1 is equal to 512 kilojoules. The processes are as follows. Process 1 to 2, compression with PV equal to constant, 2, P2 equal to 2 bar, and U2 is equal to 690 kilojoule. Process 2 to 3, W23 is equal to 0, Q23 is equal to minus 150 kilojoules. Process 3 to 1, where W31 is equal to plus 50 kilojoules. Now you need to neglect K and P changes. Determine the heat interactions Q12 and Q31. Since your question is to find Q12, that means it involves the process 1 to 2, and this the answer to this question will be found when you start to deal with the process 3 to 1. Now I have just written down all the data which is available from this problem. P1 is equal to 1 bar, P2 is equal to 2 bar. I have just converted this pressures from bar to kilopascal, and this U2 minus U1 I have found at 178 kilojoules. Now, which is du 1 to 2. That means for the process 1 to 2, the change of internal energy is found to be 178 kilojoules. Now, applying the first law here, we can get this equation. So we can write 178. But the question is, when we are trying to find the value of du, we also need to know the value of this work done. So for this process, PV is equal to constant. Now if you remember, whenever in a process PV is equal to constant, it refers to an isothermal process. That means PV is equal to RT, and if PV is constant, then RT is equal to constant. R is itself a constant, so the temperature also remains constant. So this is valid for an ideal gas. Okay, still so we are talking about an isothermal process. So work done in isothermal process can be written down by the formula P1 V1 into ln V2 by V1. So let me just write down the formula. So the work done for an isothermal process 1 to 2 can be given by this formula P1 V1 ln V2 by V1, which is equal to which can be also written as P1 V1 ln P1 by P2. Since P1 V1 is equal to P2 V2 for this process, as PV is equal to constant, it is already given in the problem, we can understand that V2 by V1 will be obviously equal to P1 by P2. So we know the values of P1, P2, we know the values of V1. So if you put the values which is given here, we will get an answer of 103.95 kilojoules. Okay, so we will get an answer of 103.95 kilojoules. So the work done for this process 1 to 2 can be easily calculated by this process. Okay, so now since we have got this data, we can, so let me just clear these things so it becomes so you can understand it clearly, you can view it very much clearly. So it will be 103.95. Okay, so I'm just removing this part here. So ultimately you will get it is 10.95, right? So it will be 74.05 kilojoule. So 74 kilojoule 74.05 of kilojoules heat has been transferred into the system. Okay, so by this formula we can easily calculate the heat transfer for the process 1 to 2. Now our question is to calculate this Q31. So I'll be again applying the first law of thermodynamics for this process, and let us see what happens there. So let me give me some time to write down the formula here. So as you can see here, I have written down the formula for this uh, process 3 to 1. So I have just written down the first law of thermodynamics for the process 3 to 1. Now it can be seen here that dq3 to 1 is equal to du3 to 1 plus dw3 to 1. Now the change of internal energy can be written down like this. The internal energy at the final state, which is the state 1, and we are talking about the initial state as the state 3. So u1 minus u3 plus dw31. Now it is already given in the problem w31 is equal to 50 kilojoule. So I have just written that 50 kilojoule. Now see, it is already given in the problem u1 as 512 kilojoule. So I can write 512 here, so which is already available. Now the problem is we don't know the value of this u3. It is not given here. So we need to calculate the value of this u3 from using the first law of thermodynamics again, and then after that only we can find out the value of this dq321. So how we can find the value of u3? It is quite simple. So let us apply the first law of thermodynamics for the process uh, 2 to 3. Okay, so as you can see, I have just written down the first law of thermodynamics for the process 2 to 3. So here it goes. Now this dq for process 2 to 3 is given as minus 150 kilojoule. So it is already provided in the problem. This W23 is 0, which I have just written here. So let us remove this because it is not going to help in our calculations. So if our equation is something like that, u3 minus u2 is equal to minus 150, then we can easily find out that u3 will be equal to u2 minus 150. There is simple mathematics. So when we are doing the calculations of u2 minus 150, it will give us a value of 540 kilojoule. Okay, so we are getting the value of 540 kilojoule. Now if we put it here, uh, then we will get, it will be 540. So it will be minus 28, and minus 28 plus 50, it will be 22 kilojoule. So for the process 3 to 1, the heat transfer will be 22 kilojoule. So it is quite easy to understand. There is another way. Okay, since we know that the change of internal energy will be 0 for the cyclic process, we can also do the same by using the uh, property of, we know this relationship, right? So du is equal to 0, right? Now for, so let us try to solve this problem from this way. So I have told you that since internal energy is a property, it is quite evident that for any property, when a system is undergoing a thermodynamic cycle, the net change in the property will be 0, because the initial states and the final states are the same. So if we illustrate this equation, we can write du 1 to 2 plus du 2 to 3 plus du 3 to 1. So that means we are writing down all the change of internal energies for all the three different processes. Okay, which will be which will add up to 0 ultimately. So for process for process 1 to 2, the change of internal energy is 178 kilojoule. Now so this is 178 kilojoule. Now this can be calculated from the second law of thermodynamics, since we know that minus 150, 150 is the Q23. So Q23 will be equal to du23 plus W23, which is 0. So at the end of the day, you can easily find that this du23 is going to be minus 50. So it will be minus 150, right? So now we can write this one as u3, I'm sorry, it has to be written as u1 minus U3, because we are always writing in the format of final state minus initial state. So here you can see 178 minus 150. You know the value of U1, it was 512. So 512, and so let us just remove these things so it will be quite clear to you. So it is 28, right? So I am removing this and just putting the value of 28 here. So this is U1 minus U3 is equal to 0. So that gives you U3 as 540 kilojoules. So this U3 can be calculated in these two different ways. Okay, that was what I was trying to show you. Okay, so let us end this here, mm, and move on to the next problem, the problem number 5. So as you can see, the problem number 5. So a gas undergoes a thermodynamic cycle consisting of the following processes. Process 1 to 2, constant pressure, where P is equal to 1.4 bar, which I have written it here. And this can be graphically represented by a straight line so that the pressure remains constant. Okay, so it is as simple as it gets. So straight line parallel to the volume axis, which refers a constant pressure process where the pressure is 1.4 bar. I have just written it into kilopascal, and the volume 1 at state 1 is 0.028, right? So it will be 0.028 and the unit will be meter cube, right? Okay, and the work done for this process, dw1 to 2 will be equal to 10.5 kilojoule. It will be 10.5 kilojoule. So it is very simple. Now for the next process, when PV is equal to constant, it refers to an isothermal process. Now you know from the concept of ideal gas, you know this graph, and you know the concept of rectangular hyperbola also. So if you treat P as X and V as Y, you are quite related with this equation xy equal to constant, which is an equation for the rectangular hyperbola, which can be expressed by this kind of graph. Okay, so it is a curve which represents PV equal to constant, right? And for the next process, that is process 3 to 1, it is mentioned that it is an isochoric process or constant volume process. So it will be a straight line which will be parallel to the pressure axis, right? So I have just drawn a straight line here so that it constitutes a thermodynamic cycle, so that the initial state and the final states are same. Now we have already done the first problem, sketch the cycle on a PV diagram. Now the second problem is that you need to calculate the net work for the cycle in kilojoule. So before going into that part, we will try to find out the individual work transfer and heat transfer for the individual processes. So to calculate the work transfer and heat transfer for the individual processes, we need to know the change of internal energy. Now as you can see, for the process 2 to 3, it is given as U3 is equal to U2. That means there is no change of internal energy, right? It is an isothermal process. You must remember it. For an isothermal process, since the temperature remains constant and internal energy entirely depends on temperature, if there is no change of temperature, then for isothermal process there will be no change of internal energy. So from that understanding, it can be also done. So let us see. So as it is given in the problem itself, U1 minus U3 is minus 26.4 kilojoule. This refers to the change of internal energy for the process 3 to 1. So we have found out the change of internal energies for these two separate processes, but we still haven't found out the change of internal energy for the process 1 to 2. No, so to find that data, we need to use the basic concept which I have just told you in the previous problem. You know that cyclic integral of any property is 0. That means summation of all the internal energies changes for the three different processes has to be 0. So we can write du 1 to 2 will be equal to minus of du 2 to 3 and du 3 to 1, right? So it will be minus 26.4, because the other, for the other one it is already 0, so it will be 26.4 kilojoule. So let us just write that, because it will help us afterwards. So I hope you have understood this problem. Summation of all the internal energy changes needs to be 0 for any thermodynamic property. Since internal energy is a thermodynamic property, the summation of all the internal energy changes for all the processes will be 0. Since du1 plus 2 will be since du1 to 2 plus du2 to 3 plus du3 to 1 will be 0, it can be simply shown that du1 to 2 will be equal to this. So let us write this value once again, because it will help us afterwards. So this du1 to 2 becomes 26.4 kilojoules. Now let us apply this information um, to find the heat transfer for the process 1 to 2. Now we know this simple information: dq 1 to 2 will be equal to du 1 to 2. I am writing this thermodynamic equation for each time, because I hope that by writing these equations you will be used to it and you will never forget the terms. Okay, though it is very simple, if you have the concept you can do it at any time, but still it is better to write down. So du1 to 2 is 26.4 kilojoules, and the heat work transfer is given as 10.5 kilojoule. So we can add it up and we'll find it will be 36.9 kilojoule. So let us take this information and write it down here. So dq 1 to 2 is equal to 36.9 kilojoule. Okay, and dw is already given to you. So now let us apply this equation to the next thermodynamic process. Okay, so I am just going to change this subscript so that it becomes it consumes a lesser time here. So it will be 2 to 3, it will be 2 to 3, and it will be also 2 to 3. Now it is already given that u3 is equal to u2. That means there is no change of internal energy here. So this becomes 0. And you have dq2 to 3 is equal to dw2 to 3. So you need to find out the work transfer here. Since it is an isothermal process, you know that it can be found out by the formula. We can find out dw2 to 3 by the formula. So you can write, you can see that the work done for the process 2 to 3 is given by this formula: p2 v2 ln v3 by v2. Now as we have written the formula. Now the question comes, do we have all the informations? We know we don't know what is the value of, sorry, we know the value of P2, which is 140 kilopascal, but we don't know the value of V2. We do understand that from the graph this V3 is equal to V1. So instead of V3 we can write V1 here so that it becomes easy to understand. Since we know the value of V1, but the only unknown which we have presently is the V2. So we need to find out the V2. Now how we can find V2? Can you tell me? So it is very easy. Actually for the process 1 to 2, the work transfer was given to you, right? So the work transfer was given to you as 10.5 kilojoule. Now since this is an isobaric process, you must understand that it will be following the formula V2 minus V1, right? So if you are able to understand this, then so from this equation you know PC as 1.4 bar, that is 140 kilopascal, and V2 is the unknown here, but V1 is 0.028, you write, which is equal to 10.5. So calculating this equation or solving this equation, you will find V2 as 0.103 meter cube. Now you have found out the value of the volume at state 2. Okay, since you have found out the value of V2, you can put it here. It is this V1. So you know P2 as 140, you know V2 as 0.103, and you need to do a logarithm of ln 0.028 divided by 0.103. So calculating this, you will find a value of minus 18.78 kilojoule. So the work done for the process and 2 to 3 you will find as 18.78 joule, right? So let us write down this data here. I'm just removing this thermodynamic graph. Okay, so also I am removing this. So now you have the heat transfer for process 1 to 2 and heat transfer for the process 2 to 3, but still you don't have the heat transfer for process 3 to 1 or the work transfer for the process 3 to 1. So I'm sorry, it will be dq. So let me write once. So dq 3 to, I'm very sorry, I am just taking extra time here, I'm very sorry. So dq 2 to 3 will be equal to dw dw 2 3, which is equal to dw 2 to 3, which will be equal to minus 18.78 kilojoule, right? So now you have found out the values of dq 2 to 3 and dw 2 to 3. Now the question comes, how can we find the next one, right? So we need to find out the heat transfer and work transfer for the next process. So this is a constant volume process, which indicates this dw321 should be 0, right? since dw321 is 0, then it is quite evident that dq321 will be equal to du321, which is given as minus 26.4 kilojoule. Okay, so you have found out all the values which were required to you. Now uh, now our objective is to sum all of this data. Okay, now our primary objective is to sum up all this data here. Now see, I am just finding out all the data is available or not. So let us remove this. Let us clear up all of this. Okay, so sum up the work done. So for process 1 to 2, it will be plus 10.5. For process 2 to 3, it will be minus 18.78. Okay, so which becomes minus 8.28 kilojoules. Okay, and if we sum up the heat transfer for this thermodynamic cycle, we will see it will be Q1 to 2, which is 36.9, you have 36.9 here. For dq 2 to 3, that means the heat transfer for the process 2 to 3, it will be minus of 18.78, and for the process 3 to 1, and for the process 3 to 1, it will be minus 26.4. okay, so it will be 26.4. so ultimately you will find that the result becomes minus 8.28 kilojoule. So it is easily understandable that the summation of all the work transfer for this thermodynamic cycle equals to the all the heat transfer for this thermodynamic cycle. So I hope you have understood the problem here. So this was a little bit of complicated problem where you have to calculate it. You have to calculate a lot of information. A lot of formula was used here. Since if you have the concepts clearly, then it is very easy to understand. So the unknowns, you need to find out the unknowns sharply. Okay, so I hope that with this we have end our lecture. So what we have dealt today is a different kind of numerical problems which we generally see. So this type of problems will help you to understand where does this first law of thermodynamics applies, where what are the situations where we can apply the first law of thermodynamics. So I hope that that was easily understandable to you. Now here you can see there are 5 problems given to you, just as same as the work and heat transfer sheet. So this is an assignment provided to you. I hope that you will try this, you will try out these problems which will um, um, gather your concepts in a much better way, which will brush up your concepts in a much sharper way. I bet it will be an interesting experience for you. So thank you and goodbye for today. We'll in the next class we'll be discussing first law of thermodynamics, but for open system. Till now we have discussed for the closed system. In the next lecture session we'll be discussing about the first law of thermodynamics, but it will be applied for open system. So till then, goodbye. Thank you for watching. Okay, goodbye.